Good day and welcome back for part 2 of our discussion on trig integrals. In the first part of our discussion, we focused in on integrating powers of sine and cosine. In this video, we're going to see if we can slightly modify our previous technique to evaluate integrals involving powers of tangent and secant. And the two examples that you see here hopefully give you the instructions that you need to evaluate the integrals. During the first part of our discussion, you most likely noticed that certain trig identities play an important role. The same is certainly true here. We need to make sure that we know the secant-tangent version of the Pythagorean identities. So note, I think students typically are able to very quickly recall the Pythagorean identity cosine squared plus sine squared equals 1. But what I want to note is there's an alternative version of this, which is equivalent, involving tangents and secants. And if you remember this version, you can always modify it slightly to get the other version. If we simply divide each and every term by cosine squared, then what you are left with is simply working from left to right, 1 plus tangent squared is equal to secant squared. So that is a trig identity we should make sure we are familiar with. So looking at the integral that we are evaluating, tangent to the fourth, secant to the fourth. And the suggested method of approach is to essentially use the substitution u equals tangent of x. So let's see if we can think our way through this. If we're going to let u be equal to tangent of x, that requires du to be secant squared x dx. So modifying our previous approach, we're thinking we need to save something to be our du. So I'm going to pull off one of these secant squared. So secant to the fourth can be written as secant squared times secant squared. The secant squared x dx is going to play the role of our du. So every other term has to be written so that it only involves tangents so that we can make the desired substitution. But note, along with the hint is the reminder of this Pythagorean identity. We can rewrite the secant squared as 1 plus tangent squared. And once we do that, we will be able to make the desired substitution. So rewriting, we have tangent to the fourth times 1 plus tangent squared times secant squared x dx. So putting everything now in terms of u's. The tangent to the fourth is u to the fourth. Tangent squared is u squared. Secant squared x dx becomes du. So note in this case, because of the even power of secant, we were able to save a secant squared and use the Pythagorean identity to write the remaining secants in terms of tangents. Now we can evaluate. So distributing through the u to the fourth, I'm going to write it as u to the sixth plus u to the fourth. And then we anti-differentiate term by term. So we have 1/7 u to the seventh plus 1/5 u to the fifth plus c. And now that we've done all of the hard work, we resubstitute and replace each u with a tangent. So this would be 1/7 tangent to the seventh plus 1/5 tangent to the fifth plus c. And in our next video, we will summarize this method a bit more generally, but for now, let me go ahead and just reiterate the previous comments. Because of the even power of secant, we are able to save a secant squared dx to be our du, write the remaining secants in terms of tangents, and use the substitution u equals tangent of x. So let's go ahead and consider the next problem where we do not have an even power of secant. And in this problem, if we follow the suggestion, It's to let u be equal to secant of x. So let's kind of just think our way through this. If u is equal to secant, that requires du to be secant tangent. Looking at our integrand, that's telling us we need to pull off one of the tangents and one of the secants to play the role of our du. So I'm going to simply rewrite this algebraically. So tangent cubed can be rewritten as tangent squared times tangent. Secant to the fifth can be written as secant to the fourth times secant to the first. So we're pulling off a secant and a tangent to play the role of du. That forces us to write any remaining tangents solely in terms of secants. And this is where that Pythagorean identity comes in handy again. And it's worth noting that procedurally, we're really taking the same approach that we've been doing in this entire section. Pulling off something to be a du, rewriting something else was a Pythagorean identity. In this case, we're going to replace that tangent squared in our integrand with a secant squared minus 1. So we would have secant squared minus 1 multiplied by secant to the fourth times secant tangent. Now we're good to go with our substitution. The secant squared is u squared, secant to the fourth is u to the fourth, and the secant tangent dx is simply du. And note, once again, we have an extremely reasonable integral left over to evaluate. And just to kind of emphasize what we've done here, because this power of tangent is odd, we can pull off one of the tangents, and one of the secants as well, but the key thing is the odd tangent allows us to pull off one of the tangents to form our du, and then the remaining even power of tangents can be rewritten with the Pythagorean identity. So note, this approach can be applied whenever we have this odd power of tangent, as long as we have at least one secant to help form the du. So with that in mind, let's go ahead and finish up the easier part of this problem. Distributing through the u to the fourth, we can now anti-differentiate term by term, and then resubstitute. And this finishes up the current video. But remember, if we were meeting in class, I would be having you work on pages 3 and 4 of the note handout. What we've seen on this page of the note handout is a procedure we can use to evaluate integrals involving powers of tangent and secant, where in the second case the power of tangent was odd, and in the first case when the power of secant happened to be even. So in problem number 3 in the note handout on the next page, you're asked to summarize this. So before viewing the next video, just give yourselves a few minutes and see if you can summarize these key results a bit more generally. So stay tuned and take care.